In my Structural Engineering Made Simple series, today I talk about cladding support and Girt design. Please take a moment and read the disclaimer at the bottom of this page before we continue. Cladding, such as prefabricated panels and metal sidings, are often used as part of the facades in buildings. Claddings are exposed to wind loads, and as such, they must be able to transfer the wind forces safely to the structural backup system and framing. In certain situations, and especially when the cladding spans in the vertical direction, the backup system is not able to fully support the cladding against the wind load. To clarify, let's examine this in a cladding detail. This is an example of metal siding used as the facade. As you can see here, the cladding runs in the vertical direction. This detail shows how such a cladding can be attached to the backup system. The support for the cladding in this case is only at the two floor levels, or at the roof and the next floor below it. As you can see in here, we have a metal cladding. There is a backup 8-inch metal studs. The metal studs are attached to the structural system. What you see here called the main beam with this cross section is at the roof level, and this is the beam at the floor level. The metal studs are attached to the structure through the roof and through the floor level in this case. When the wind pressure is large enough, the metal studs and cladding may bend in the vertical direction as demonstrated in this figure. As you can see here, the cladding is damaged because of the bending. The metal stud is also under bending. To prevent this situation, a support beam, which is called the Girt, in the form of a W section, a channel, or a tubular square section is used in the mid-height as an extra support. As you can see in here, by providing this Girt, we have eliminated the deformation of the cladding. Also notice that we have in this special case used a W section with a strong axis in the vertical direction. This is because it is taking the wind loads coming horizontally. We also have a sag rod system as shown in here that we'll talk about it later. The sag rods are attached in one end to the girth, the other end to the structural system. As expected, this beam, which is called the girth, is positioned in such a way to resist the bending in its strong axis, as you saw in this figure. Design considerations. Some claddings are able to support themselves, and as such they do not need girts. Examples of these are reinforced concrete precast facade panels. Let's put back our detail again. As shown in the detail, sag rods are required to support the girts to prevent lateral buckling. In this special case, we are using rods with 5/8 inch of diameter. Usually 2 sag rods are used over the span length of the girth. Let's put back a detail in here. As you can see, there are 2 sag rods used along the length of the girth. Because the girth will be under bending in its weak axis supporting its own weight, in a way sag rods act as supports, and as such the girth becomes like a 3-span continuous beam. In this way, its bending span will be reduced, as shown in this figure. The self-weight of the girth is applied vertically downward, and this creates tension forces in the sag rods. And the idealization as a 3-span beam under the self-weight of the girth is shown in the next slide. So here is our system again, which can be shown as a 3-span beam under the self-weight of the girth. The reaction that you see here in the middle supports these reactions are actually the tension forces in the sag rods. Let's continue with design considerations. However, when designing a girth for the wind load, we use a simply supported beam with a span length L. As you can see in here, the wind load is a horizontal force acting on the girth. The girth would act like a simply supported beam. For the load shown, it would bend like this, with support at this column and another support at this column. The length of the beam is equal to L. The load from wind is uniformly distributed on the girth with proper consideration for the tributary width of the wind pressure. By tributary width, we mean the spacing between the girths in the vertical direction. Let's continue with design considerations. As we discussed before, we need sag rods. A sag rod is more critical for buckling and the compression force causing it. And you might say, just a few minutes ago, we talked about the tension force in the sag rod. So what are these compression forces? Well, because of the potential for lateral buckling of the girth, there may be compression forces developed in the sag rods as well. According to Professor Joseph Ura of the University of Texas, the compression force is about 1% of the compression force that is developed in the flange of the girth as a result of the wind pressure. We're going to look at this a little bit later. This compression force is compensated by the tension in the sag rods because of the weight, as we discussed before. If the compression force is not fully compensated with the tension force, then the difference must be smaller than the buckling strength of the sag rod. And we'll have again coming up this a little bit later in an example problem. Continuing with design considerations. In situations when the adjacent columns are far from each other, a large size girth will be needed. This makes the design very uneconomical and unreasonable. The solution is that to make the situations more economical, the solution is to add additional columns in the perimeter of the building to shorten the span length of girths. These additional columns are sometimes called wind columns or soldier columns. In the foregoing details, we use a W section positions on its side. However, a channel laid flat on its side, a hollow square section, or Z profiles are also used as girths. In seismic areas, consult with the relevant local code to find out whether special provisions for design are required. However, most designers believe the design for wind is adequate enough for girths. This photo shows girths in a building. You see two girths marked in here. We have a main frame made up of gable roof system, and you'll see a couple of columns in here. These are providing additional supports for girths, and therefore we call them as wind columns. Let's look at an example. The span length of the girth is 24 feet as shown in this figure. That is the spacing between the two adjacent columns. The tributary width for wind, spacing between girths in the vertical direction, as we talked about, is 18 feet. And the total wind pressure is 20 pounds per square foot. Now, this total pressure considers any pressure from one side with the effect of suction from the other side, etc. We are using a W8 by 18, so the self weight of the girth is 18 pounds per linear foot. The yield capacity of this section is 50 KSI, and we are using sag rods which are 5/8 of an inch in diameter, and the length of each sag rod is 12.6 feet. Now what we are talking about is the length in the vertical direction from the point these sag rods are attached to the girth to the point that they are attached to the structural system in the upper level. So the 12 feet we are talking about is pretty much the length of each sag rod. As you can see here, we have shown the wind load applied horizontally on the girth. In this problem, we will be using the allowable stress design method of the American Institute of Steel Construction. And for example, you can look at the AISC 13th edition. That is the one we have used in this problem. But you can equally use other editions as well. And the requirement is only to look at the bending capacity of the girth and also the buckling capacity of the sag rod. These are the two areas that we need the code for. Well, let's find the wind pressure applied on the girth. It's a uniformly distributed load. You recall that the wind pressure on a square foot was 20. Tributary width was 18. Therefore, we are talking about 360 pounds per linear foot. Because the girth is considered as a simply supported beam, the maximum moment is QL squared over 8, and plugging the value for Q and L and in the equation for Q and L in the equation, we come up with 25,920 foot-pounds. That is the applied bending moment. Because the girth is attached on its compression flange to the cladding in multiple places, we can assume the compression flange is fully supported laterally, and as such the bending resistance of this section, this W8 by 18, can be obtained from AISC, assuming fully supported laterally, and the value is listed at the bottom of page 3-77 of the 13th edition of AISC, and it's called MR. That's the resisting moment allowable. That's 26.5 foot kips, which is 26,500 foot-pounds, and certainly this is larger than the applied moment. Therefore, this W8 by 18 is okay. So we are okay as far as the size of the girth is concerned. Now let's look at the sag rods. The critical force in each sag rod as a compression force is 1% of the compression force in the flange of the girth due to wind load. So we'll demonstrate that here. The easiest way to find this compression force is to resolve the moment into a couple, into two forces, a tension and compression. Using this approximate equation, moment divided by D. D is the depth of the cross section of the girth, which is 8 inches. It's 8 by 18, so it's 8 inches. So converting the moment into inch pounds, dividing it by 8, which is the lever arm, which is D. So that is our D. We'll find out the total compression as 38,880. However, there are two sag rods, so let's divide it by 2. We get 19,440. But let's just show this momentarily so you see what we are talking about. And we are considering the fact that wind is acting in this direction. Therefore, we'll have a compression and we have a tension. You see the lever arm, the depth of the cross section for the moments that is shown in here. And by dividing the moment by D, we'll get these forces F. And however, remember that we only need 1% of these as a compression force in each rod, as we discussed it before. So let's multiply this value by 0.01, and that gives you the compression force in each sag rod, 194.4. Now we also need to find the tension force because of the self-weight of the gird there. So let's examine that. Remember that we said under the self-weight, the gird can be considered as a three-span beam. So I show the figure again. And this value is really the tension force in the sag rod. What is Q? Q is the self-weight of the gird, which is 18 pounds per linear foot. Putting that in the equation, considering the length, which is L equal to 24, we come up with 158.4 pounds of tension force in a sag rod. So you're talking about a compression force that we computed before, and now we'll talk about a tension force. So you found out the difference of the two, and that's the net compression in the sag rod. If it happens that tension is more than compression, then we don't do anything about the sag rod. They are fine, they are under tension. But in this case, as you see, we are talking about a net compression of 36. This was a compression, this was a tension. The difference is 36 pounds. It doesn't look much. Nevertheless, we must make sure that this is smaller than the buckling strength of the rod. How do we find the buckling strength of the rod? First, we need to find the allowable stress for compression, multiplied then by the cross-sectional area. We'll get the allowable buckling strength. And A sub B is the cross-sectional area of the rod. With 5/8 of an inch diameter, the cross-sectional area is 0.31. We also need to find the slenderness ratio for the sag rod. The slenderness ratio needed for the computation of buckling strength, we'll take K equal to 1. K depends on the end condition. Since we simply bolt the sag rod to the structural members, K is equal to 1. L is the length, which is 12.6 feet. And R is the radius of gyration of the cross-section of the rod. And we consider a small circle with 5/8 of an inch in diameter. The radius of gyration is 0.16. And that gives us the slenderness ratio. As you can see, it's pretty large. So we consult with the AISC. Section J 4.4 talks about how to find the buckling strength of members that have a very large slenderness ratio. And actually we follow the provision in section E of the AISC. And first we find FE. FE is a critical stress causing buckling, or Euler stress. It's a familiar equation, pi squared E divided by KL over R squared, where E is the modulus of elasticity, 29 million psi. Plugging numbers there, we have FE equal to 320.5 psi. Now, following AISC procedures, the allowable compression strength is equal to 0.877 FE divided by omega C. Omega C is a factor of safety, which is 1.67, and that gives us the allowable compressive strength of 168.3. Now I multiply this by the area, and I get 52.2 pounds compressive strength of this member, or buckling strength, which, as you can see, is larger than 36, which was the applied compression. Therefore, our sag rod is okay. In closing up the discussion, I thought maybe it's a good idea to talk about causes and signs of damage in such facades. The potential damage causes could be the following. A main cause of damage in girts is an inappropriate design. This may stem from lack of sag rods to prevent girt movement. You saw the importance of sag rods. Using an inadequate structural member for the girt. Inadequate connection of the girt to the supporting columns. Excessive corrosion of the girth could be another damaging issue. Inadequate cladding connection to the girth could be another one. Signs of damage, deformed metal siding open at seams, connection elements missing, etc. Corrosion stains appearing on the cladding. Cracked or displaced claddings are visible. And when we have glass panes, you may find breakage of the glass panes, which indicates deformation of the cladding. So what are the repair options? In most cases, the facade and its elements, cladding, curtain walls, will need to be removed to examine the condition of the girts. Necessary action include the girt redesign and implementation of proper detailing and installing those sac rods. Generally, girts are designed against the wind load transferred from the cladding, as we saw in our example. In seismic cases, it is a good idea, in seismic areas, it is a good idea to consult with the local code to decide whether certain provisions for design and detailing will need to be followed in compliance with the code. Thank you for watching this video.